In this video, we're going to be talking about scatter plots, lines of best fit, and correlation. So let's first just think about, a scatter plot. What is a scatter plot? I'm sure you've seen one before, but let's really think about what it is and how we'd even come up with one. So imagine you want to know if there's a relationship between studying for the GRE and your GRE score. Okay, well, let's ask people these two questions. We're going to ask people, one, what was your GRE score? And two, how many hours did you study for the GRE? So if we were to graph this, and let's say this x-axis has the number of hours studied, and the y-axis has the GRE score. And let's say a person that we asked told us that they studied for 10 hours. Their GRE score was, on math was a 150. That's a data point. So notice each data point is a person. And notice that because each data point has an x value and a y value, that's two different answers that that person gave you, right? Let's say that you asked somebody else and they studied more hours and they got a higher score, then they'd be maybe somewhere here, right? And let's say we asked a bunch of people and, they might overall follow a certain trend, but you might have some people who are anomalies, right? Like somebody who studied a lot but didn't score so well, they might be here. Somebody who studied only 1 hour but got a really high score might be here, and so on. So this is a scatter plot, right? So it's visualizing a relationship between two variables, and each data point is a person. Now, looking at this scatter plot, what do we make of it? Now, line of best fit, or regression line, is something that it's basically the most popular tool for analyzing a scatter plot. And so looking at this, if we were to try to come up with a line that best fits these data points, then, you might guess that it looks something like that. Now, there's a lot of, so here's where the calculus and the crazy sort of math comes in for minimizing the sum of squared errors. Thankfully, for the most part, you don't have to worry about any of that in order to at least understand conceptually what's going on here. But there's a lot of math that goes beyond, that goes into determining how exactly should we determine what that line is. Now, just to take a slight detour here, what is a line? Now, a line essentially is something that takes the form y equals mx plus b, right? So y equals mx plus b. So again, what is this? What is y equals mx plus b? Well, this is your x variable, this is your y variable, and the m and the b are constants. So essentially, this b is what we call the y-intercept. The b is the y-intercept. And it's essentially the value of y when x is 0. So if x were 0, then whatever that is. So let's say here, if the best regression line here, this best line of best fit, started off here at a score of 130, well, then that's our b. So 130. This m is called the slope. And the interpretation of the slope is essentially saying how much, so I'll just write this out here, the slope is the increase or decrease, if it's negative, increase or decrease in y when x goes up by 1. So really what it's saying is, when you study for 1 more hour, how much does your GRE score, on average, change by? So that's what this is saying. So notice if your score is going up the more you study, well then your m, your slope, is going to be a positive number. And if it goes down, then it's going to be a negative number. So just to recap so far, any line in the world can be expressed in the form of y equals mx plus b, where x and y are your two variables, and m and b are constants. They're specific numbers for any given line. That's what distinguishes one line from another, is what value of m and b do they have. So let's say this, the line of best fit, happens to be, let's say for this example, y equals 10x plus 130. All right, so what that would mean is that for every hour, you're getting 10, your score goes up by 10. For every extra hour that you study, your score goes up by 10. That's what that means. So now, again, how do you determine what numbers you should put when you just have a scatter plot? And the good news is whatever software you're using, Stata, for example, will basically tell you that. It'll tell you that, and there is a mathematical way to find that, we'll leave that to the statisticians to figure that out. But basically, that's how you can find the best slope, the best intercept to best fit these data points. So now, looking at this slope, the steeper it is, the steeper the line is, the bigger the slope is going to be, right? That's sort of saying that, x and y are more, y is more sensitive to x, right? So the bigger the slope is, that means that y changes by more when x goes up. Now, that being said, this y equals mx plus b notation, that's usually what you see in grade school. But when you go into the world of statistics and regression and econometrics, which is where we're going with this, they just use slightly different notation. Instead of calling it m and b, it's usually reported like this: y equals beta 0 plus beta 1x, where this beta 0 is the intercept. So if you're used to mx plus b, the beta 0, this is the intercept. And this beta 1, this is the slope. It's the number that's multiplied to x. So again, this is just notation that you might see in a book, but for a specific instance, for a specific graph, you won't see the letters, the Greek letters beta 0 and beta 1. You'll see numbers in its place, right? Or when you, use your software with a bunch of data points to find the slope and the intercept, you'll just get numbers for the slope and the intercept. That being said, there's this other thing called the correlation coefficient. So again, just to summarize here, you have a bunch of data points, right? Each data point's a person. That's a scatter plot. You could put a line through it, the line of best fit. You could interpret that line by looking at the slope primarily and saying, oh yeah, when x goes up by 1, y goes up or down by whatever the slope is, and it's a positive slope if it goes up, negative slope if it goes down. The bigger the slope and magnitude, the steeper it is. And the last sort of thing about this is this thing called the correlation coefficient, R. So whenever you have a scatter plot and a line of best fit through it, in addition to the slope, you can also get this thing called the correlation coefficient, R. So R is the correlation coefficient. And the correlation coefficient is a number between -1 and 1. So it's a number between -1 and 1. So between -1 and 1. Unlike the slope could be 45, for example, but the correlation coefficient, the most it could be is 1, and the least it could be is -1. Now, whether it's and whether this is positive or negative, in the positive range or the negative range, it's basically also just like the slope based on whether it's going up or down or not. So essentially, if R is positive, greater than 0, then that means the slope beta 1 is also going to be positive, and it's an upward slope. And same with if it's a downward slope. If R is negative, then your slope is negative. So they'll always have the same sign. That's going to have a downward slope. Okay? So that's what's going on here. Now, what though makes the correlation coefficient, what makes it strongly correlated or not, or weakly correlated? Well, that's the difference between slope and correlation coefficient is this, is that the slope, your beta 1, is about steepness versus your R, your correlation coefficient, is about fit. So it's sort of like this. If you have data points that sort of look like this, where they're sort of all over the place, and they have like a really like a high slope, then here you're going to have a high, your beta 1 is going to be high, but your R is going to be low, as opposed to something like this. Here, basically, the closer all the points, the data points fall into a straight line, the closer they fall into a straight line, doesn't matter the slope of the line, the closer they are to a straight line, the bigger the R is. So here, this is going to have a high R, but because it's not as steep, this slope isn't as steep as this one, so it has the beta 1 is going to be relatively lower. And of course, you could imagine all possible combinations with that, right? If you have a really, you could have a steep one that they all fit into a straight line, and that's going to be both the slope is high and the correlation coefficient's high, you know. And if it's just a weak slope, but you know, it's all over the place and they're both low. In general, if there's no relationship, right? So if there's no relationship, if the data points basically look like this, like where there's no relationship at all, if the line of best fit is a flat line, if the line of best fit is a flat line, then there is no relationship here, right? The R is 0 and your slope is 0, right? So basically, and that's one thing throughout this statistics, regression, throughout all this, one of the main sort of things that we end up looking for when we do regression, when we use data and things like that to find out what the slope is to check if it's 0 or not. Because if the slope is 0, how would you interpret this? If you were to ask people, how many hours did you study, what was your GRE score, and your data points looked like this, and the line of best fit was a flat line, the interpretation there is basically, even if you study for more hours, your expected score is the same. And so ultimately, that's like saying there's no relationship between these two variables, that as one goes up, the other doesn't even systematically go up, it doesn't even systematically go down. There's just no relationship at all. It just, we have no additional information about GRE score when we know how many hours you've studied. That's what it would mean if the slope is 0, and the correlation coefficient is 0 as well in that case. Right? So that's one thing we're going to be looking out for, and that's why one of the main themes is these hypotheses tests that we're going to do is really just to check, is the slope 0 or not? Because the meaning of a 0 slope is no relationship between these two variables. Now, one sort of, and so just while we're here, of course, I know I've said this verbally, but just so you can visualize it, if the data points did somehow look like this, you know, where the more you study, the lower your GRE score, well then, it's going to be like this. The line of best fit's going to be a downward slope, and so your slope and your correlation coefficient R are both going to be negative numbers. But notice here, if the data points all like still fit into a straight line, here, if somebody were to say, try to estimate the correlation coefficient over here, all right, the R. Well, remember, correlation coefficient R, that's not about steepness. That's just about, hey, how good of a job is this doing at fitting into a straight line? And it's doing a pretty good job, you know, like maybe like a 0.9 out of 1, because remember, it's basically out of 1. So it's like, yeah, you could say something like 0.9 or 0.8 or whatever, right? Something pretty close to 1. And so if you think it's doing a pretty good job, unlike this guy, they're not quite as into on the straight line as these guys are. And so here you might say R is like 0.4 or something, right? So here you might say R is approximately 0.4. Here you might say R is approximately 0.9, except notice it's a negative slope, so not 0.9, but negative 0.9. So again, just to recap, how does correlation coefficient R work? Whenever you have a scatter plot, upward correlation coefficient means upward slope means it's a positive correlation coefficient. Negative is downward slope. 0 if there's no relationship at all. And the closer that number is to 1 or negative 1 is if the data points fall neatly into the neater they fall into a straight line, the closer that is to 1 or negative 1. Finally, speaking of R, in addition to correlation coefficient, there's also one more called the coefficient of determination. Most people, even people who do stats regularly, often they're like, wait, what's the coefficient of determination? That language isn't as commonly used, but everyone who does stats will know what it actually is. The coefficient of determination is what's called R squared. R squared is literally the square of your correlation coefficient, right? So it's literally the square of the correlation coefficient. And don't worry about the capital versus lowercase. Usually, most people report it as a capital R squared, even though, but you could, lowercase r squared still means the same thing, and correlation coefficient is usually a lowercase r everywhere. But again, different books might have their different conventions, but for the most part, R is correlation coefficient, lowercase or uppercase, and R squared is the coefficient of determination. And so essentially what R squared is doing, R squared, it has a nice interpretation. So really the main usefulness of the correlation coefficient is actually as an in-between step to finding your R squared. So let's say your correlation coefficient, let's say that is R equals 0.9, okay? So again, it's like, all right, all the data points are mostly falling into that straight line. So it's like a 0.9, right? By the way, the only way correlation coefficient's actually physically 1 is if all the points are exactly on that same straight line. So even if like they're a little bit off, it won't be a perfect 1, but it might be pretty close, right? Like 0.95 or something like that, 0.99 even, right? So let's say your correlation coefficient's 0.9, and let's say that, you're now asked, what's your R squared, and interpret your R squared. All right, well, so our R squared value, which is, again, our coefficient of determination, the more important one, is, well, yeah, whatever 0.9 squared is, right, on your calculator. And so 0.9 squared on your calculator would be 0.81. Notice that's sort of the weird thing about numbers that are less than 1. Usually any number you squared, it gets bigger. But if a number is less than 1, if you square it, it actually gets smaller because you're multiplying it by a number less than 1, like 0.9 times another 0.9. So either way, it's 0.81. But in either case, notice one thing. The coefficient of determination is always positive. Well, because it's a squared, right? Squares have to be positive numbers, because any number multiplied to itself is going to be a positive. Because even if it's negative, even if R was a negative number, like let's say, for example, R was negative 0.6, well then the R squared is going to be positive 0.36, right? And so notice it's positive, and I'm going to interpret these numbers in a second, but just to make sure, so the range is between 0 and 1. So R squared, so even though R itself is between negative 1 and 1, the R squared, the coefficient of determination, is always between 0 and 1. So this, I'm just going to say here, it's always between 0 and 1. And so notice that if your r is 0, meaning there's, like I said earlier, with if it's a totally flat line, there's no relationship between these two variables, then the r is 0. Well, 0 squared is 0 as well, so then your coefficient of determination is also 0. But yeah, okay. So anyway, so let's say, just to recap, you have a scatter plot, you put the line of best fit, you could look at the slope, you can interpret it about how x is, how y is changing, how sensitive it is to x, how steep it is. You can think about the correlation coefficient, right, that number between -1 and 1, just to sort of standardize it, and that's really saying how well, not how steep it is, but how well do they fall into a straight line. And then if you just finally square that number, you now get a really nice interpretation of that. So here, I'm going to first write out what the interpretation is, and then I'm going to say why it's useful and what it means. So here, in general, whatever the r squared is, so let's say r squared is 0.181, here's how you'd interpret it. You'd say 81%. So notice that because it's between 0 and 1, that has a nice percentage interpretation, right? Because just like percentages are between 0 and 100, well, 0 and 1, it's the same thing. You just move it 2 decimals over. So 0.81 is really 81%, right? Because it's 80.81 out of 1, right? So 0.81 out of 1. So 81% of the variation in y, whatever your y variable was on the y-axis, which in our case was the GRE score. So 81% of the variation in y is explained by x, which in our case was hours studied. Now let me just say why this is a really useful interpretation. Here's a question. Why do different people get different GRE scores? Why doesn't everyone in the world get the exact same GRE score when they take that exam? And that's sort of like a really broad question, but that's in a way what a lot of economists and policymakers are trying to answer. Why do people get different GRE scores? You might have some theories about that, right? Like, oh, maybe they have different, parental incomes, and that went into how much, resources got delivered to them growing up and stuff like that. Or you could think about, maybe there's some natural ability component to it. Maybe there's a motivation component to it. Maybe it's because they studied for a different number of hours. There could be a whole host of reasons. And, you could always keep thinking of additional reasons, even if you think you've captured all of them. And the true answer is that it's probably a combination of so many different variables, not just one thing. So what we're trying to interpret here is this. So again, the question is, why do different people have different GRE scores? And this is unrealistic, but this is basically saying 81% of the variation, meaning 81% of the reason that different people have different GRE scores is because of this, or at least is explained, association-wise here, is explained by this x variable, meaning in this case by hours studied. So what this is saying is, if everybody studied for the exact same number of hours, the 81% of the differences that we observe in GRE scores would go away. There would still be some difference, right? There would still be 19% difference unexplained. But yeah, notice that if you were to add more and more x variables to your model, you're going to be able to explain more and more of that variation. So one big picture, goal of statistics, of this type of statistics regression, is to explain variation. That's what we're trying to do. We're trying to explain variation in our outcome variables, in our y variables. And so yeah, so your r squared is a really good indicator. It's a really important indicator because it's sort of telling you that, at least according to this scatter plot, what percentage of the variation is being accounted for by this one variable. So that's how you interpret r squared.